Okay, we can continue with this by saying, well, we can look at the composition of maps. I want you to be able to see this at the same time. So I'm going to have to do some window maneuvering here just so you can get, I want two windows up. Okay, so down here, what I want to do is show you how, let's compose these two maps, right? As maps. So we can say, well, we want to do G circle H of X, Y, right? It's going to act on this vector here. Well, what that's going to equal is G of H of X, Y. I've used square brackets here rather than curly ones just because we have the parentheses for the function notation. I don't want them to be too unreadable. Okay. So this is just how composition is defined. Well, what's the image of XY? Well, that is G of, and the image is the 3 vector X, Y, X plus Y, right? Then I can apply this one where R is X, S is T, and S is Y, and T is X plus Y. So this is going to be the 4-dimensional one, X, Y, and what's T? Well, T is X plus Y. And then this one is going to be all of them, X plus Y plus X plus Y. Right? Because it's R plus S plus T. R is X, S is Y, and T is X plus Y. So it's X plus Y plus T, and T is X plus Y. So there's X plus Y and X plus Y. So the map G circle H it maps X, Y to X, Y, X plus Y to X plus Y. Well, that's the map action, right? Shruti.
So I understand kind of so we did H of X, and that was just the X, Y, X plus Y.
Yes. So yeah, we just replaced H of X with X plus Y plus, and so the problem then is that when we do G, this is playing the role of R. This is playing the role of S, and this is playing the role of T. So when I come over here, I have R, S, T, and this is R, S, and T. Okay? So it turned out that I don't. So then if I then forget where they came from and just do it. So I have this stuff here, right? That's the map. Now, the question is I should then be able, well, let me then put this in, let me copy this in here that G composed with H acting on X, Y goes to X, Y, X plus Y to X plus Y. Okay, that's the result. Action of composed maps. We're going to see, can we get the same thing from multiplying G and H? Well, let's look at G here. And so what I want to do is I'll copy it down here so we can look at it at the same time. So this is looking at the matrix stuff. We have H. We want to compute G times H. Well, let's write down H first. H is 1, 0, 1, 0, 1, 1, right? And then G here is 1, 0, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1. Okay? This is G and this is H. Are you guys with me? Okay, so let's multiply these two matrices together. Well, this is a 4 by 3 times a 3 by 2 is going to be a 4 by 2, right? So the first between 1, 0, 0 times 1, 0, 1 is going to be 1, right? This is going to be then 1, 0, 0 times 0, 1, 1 is going to be 0. The second row is going to be 0, right? This one times this one, then this one times this one is 1. I'm going to need more space down here, right? So it shouldn't cut it off so quickly. There, that will probably do. Okay, so I have 1, 0, 0 times 1, 0, 1 is 1. 1, 0, 0 times 0, 1, 1 is 0, because you can see that the one, then this is 0, 1, 0 times 1, 0, 1. None of the ones match up, so I get 0, but on the second one, the middle one matches up, so I get 1. Then the third row, 0, 0, 1 times 1, 0, 1 is going to produce a 1, right? This one times this one is a 1. But then 0, 0, the third row times the second column is also going to produce a 1. Then the last one is going to, this one has all 1. So it's going to just produce the sum. Well, this is going to be 2. And this will also be 2. Okay, so you see that, does that matrix multiplication make sense? Okay, well, now we can ask, well, what is G of H times some vector V, where this is like X, Y, right? Because so I take this matrix, 1, 0, 0, 1, 1, 1, 2, 2, and multiply it by X, Y, and see what it gives me. Well, this is a 4 by 2 times a 2 by 1 is going to give me a 4 by 1 matrix, right? So it's going to be X, 1 times 0 times X, Y is X. This one's going to be 0, 1 times that. That's going to be Y. 1, 1 is going to be X plus Y. And 2, 2 times XY is going to be 2X plus 2Y is 2 times X plus Y. And you notice that this is the same up here and down below, same as from map action. This is just an example confirming that it works. That if you can actually if you have two maps, you could compose them by just their map action directly, or you could form the matrix of each one of them, multiply them, and that matrix is the representation of the composite. So you can just find the same results. Is this okay? So this is the primary role of matrix multiplication. It represents composition. So, for example, if let's say, it turns out that just think about this concretely. Let's say that you had all the spaces were the same. Like, let's say you had the map R that went from V to V. Now, that's a linear transformation. And then let's say what you did was okay, let's say that you had the map R from V to V, and then you can sort of compose it with itself to be two copies of R. Well, if this has the representation R and the representation R, then R squared would represent R composed with R. Now, let's say that this was, say, a rotation through, let's say this was a rotation through an angle theta. Let's say that you sort of had a coordinate system and you thought in the plane, you think of your vectors as arrows, and you had the representation of rotating those vectors by an angle theta is a linear transformation. It's a linear map from vectors thought of as arrows. So I could compose them. I could represent that with a matrix R here that would then produce the rotated vector. If I wanted to go through a rotation of 2 theta, I could compose these two maps, and this R times R would represent the rotation by 2 theta, twice that angle. And I could implement that by just multiplying this matrix twice. So R squared would implement that map. And we could actually, maybe it's useful at this point to make this concrete. Let's say we had R2C to R2C, and that we wanted to do XY that was, say, rotation by angle theta. Well, let's look, and we want to find here's the XY coordinates, and here's some vector V well, let me draw it twice here. We have a vector V that's at X, Y, and we want to rotate that through an angle theta. And doing it geometrically is you have to mess with some stuff, right? But so it's actually going to be easier to do this, finding this is the map. So R represents the map rotation by theta. It turns out that's a linear map, and it's useful then to find the matrix that represents that map, right? Well, let's look, because we know that the map matrix that represents this rotation, we can call it R of theta. We can find that matrix by looking at the basis action, the basis action of 1, 0, and 0, 1. So let's look at if we start off with 1 here, right? This is the vector 1, 0. It's along the x-axis. If we want to know what is if I rotate this by theta, what I have is, right, I have then, since I've rotated, it's the same length, right? And I've got this theta in here. Since I've rotated it up, if I drop this perpendicular here, I've got, this is the side of this triangle here is cosine theta, and the side here sine theta. If you remember your trigon, you have a triangle here, right? You've got the hypotenuse is length 1. You've rotated the length 1 vector on the x-axis up into this position. Then we've messed with trigonometry to see what are the coordinates of this point then are cosine theta, sine theta. That's our vector. So our map here maps 1, 0 to cosine theta, sine theta. Okay, a little bit sort of math that you didn't expect today, but so this isn't too much, right? So then we have to find the other. So this will be the first column of our matrix. Then we can look for the image of the other basis vector 0, 1. Well, that is this one here, right? 0, 1. So we want to rotate that by an angle theta. Well, here's the triangle where we've rotated it by theta. This is of length 1, right? So this side here, the side adjacent to the angle is going to be cosine theta, and this is going to be sine theta. So what is this point here? Well, if you put it back in the coordinate system here, this point here, this vector here is, this point here is on the x-axis, so that's minus sine theta, because I've come on the negative side. Then the y-coordinate is cosine theta. So if this vector goes to is minus sine theta, cosine theta. Okay, so using this principle, our matrix R of theta just equals, well, cosine theta, sine theta, minus sine theta, and cosine theta. So then you can say, okay, well, if I take R of theta times a vector xy, then that just corresponds to cosine theta minus sine theta, and sine theta cosine theta times xy, and you do the matrix multiplication, you're going to end up with x cosine theta minus, with the next coordinate minus y. Well, this would be x cosine theta minus sine theta. Then the lower component would be x sine theta plus y cosine theta. So if this was the original vector, for any vector x and y, this is the rotated vector. So to do this geometrically is complicated, right? And you can also see what happens, the rotation by 2 theta is going to be the product of these two, right? So I could make the product of these two as cosine theta minus sine theta, sine theta, cosine theta times cosine theta, sine theta minus sine theta, cosine theta, right? And so, because this one rotates it by theta, this one rotates it by theta, right? So I've said rotation by 2 theta is just, I just rotate it once and twice, right? So if I can multiply those together and get cosine theta, sine theta, no, that's not right. What I'm going to get is this row times this column is, let me get it without little squiggles, will be cosine squared theta minus sine squared theta, right? And then the other one here will be minus sine theta minus sine theta cosine theta, well, minus 2 sine theta cosine theta. And then down here, it will be sine theta cosine theta plus cosine theta sine theta will be 2 sine theta cosine theta, because they're the same terms. And over here, you'll have this, the second row times the second column will be minus sine squared theta plus cosine squared theta. You notice these are the same thing, I just wrote them differently, okay? Now, it turns out that then you can do something nice here and say, well, we could say this matrix applies for any angle theta. So we can also say that R of 2 theta equals, just take this and put in 2, it's just the cosine of 2 theta, sine of 2 theta, minus sine of 2 theta. And I think, yeah. Now, these should produce the same result, and they're going to be true if cosine of 2 theta equals cosine squared theta minus sine squared theta, which is one of those trigonometric identities for, you know, then minus sine 2 theta is equal to 2 sine theta cosine theta. So in fact, you could sort of derive these trigonometric identities by this means, okay? So the point is, these formulas that you have from trigonometry that just are weird and messy are the results of linear transformations and matrix multiplication. So all these products in here. So this whole thing with trigonometry, you can think of in a linear algebra context rather than being some arcane, stuff. And the nice thing is you get this matrix just from the basis action. You didn't have to do some fancy geometry. You just had to deal with the basis action. So now you could go and imagine, well, what if I wanted to do this in 3 dimensions? You could say, okay, I want to take a vector in 3 dimensions and take some axis and rotate it around that axis. Well, you wouldn't need to do all the geometry. You just have to find, well, what's the basis action of 3 basis vectors? Then you get the matrix for the thing that rotates any vector around some axis. Then you get that matrix, and that does that rotation. And so then, but you've got it in 3-dimensional space, which is much harder to deal with. So there's a lot of economy of geometry by translating this to a linear algebra problem for rotations. And rotations come up all the time in all kinds of mechanical engineering or graphics, if you're computer science. And all this stuff has been put into those graphics libraries that you would use. You wouldn't redirect, but anyway, you sort of understand what's going on, right? Anyway, I just wanted, this is sort of one of the sort of benefits of this, composition and other stuff with matrix multiplication. And this is a special case of matrix transformations. Okay, so let's put